quickly write down again the stiffness matrix for a bar element expressed with respect to the global axis, and how we can use that to calculate the stresses in a bar element, right? So we've already done that, so I'm just going to write it down, and I would like to point a couple of things. So this is the global stiffness matrix for a bar element. And we wrote this as K equals to T transpose multiplied by K prime multiplied by T. And we know that this K is a 4 by 4. This K prime here can be expressed as a 4 by 4 if I'm using T 4 by 4, or I can still keep it as a 2 by 2, but in this case I'm going to be using the star and the star, where this is going to be a 4 by 2 and this is going to be a 2 by 4. I defined last time, I defined the T star as a 2 by 4, where we had the CS 0, 0, 0, 0, and CS. And simply the T star transpose would be the transpose of this one. When we work this out, knowing of course that K prime for a bar element was EA over L times 1 minus 1 minus 1 and 1. We found that this K with respect to the global axis is equal to A E over L multiplied by C squared CS S squared CS. And I want to show you an easy way to remember this. This basically would repeat here. So we have it in the first quarter and then the last quarter. And then on the two other sides, we're going to have it with a negative sign. So come here and put like minus C squared, minus CS, minus CS, and minus S squared. Likewise, minus C squared, minus CS, minus CS, and minus S squared. Which if I let lambda be equal to C squared, CS, CS, S squared, I can make this K using partition matrices equal to lambda minus lambda minus lambda and lambda. before we do the example, we want to look at the computation of stresses for a bar element in the XY plane. So in the XY plane, I could have a bar that has an axis x prime that makes an angle theta with the x-axis. So we have a bar here. And this bar has two nodes, 1 and 2. And looking on the prime axis, we can solve for the element forces. If we know like F2 x prime, and here I have F1 x prime. So these are the prime element forces. So the element stiffness equations with respect to the local axis, where F1 x prime, F2 x prime equals to AE over L times 1 minus 1 minus 1 and 1 multiplied by the prime nodal displacements. So that would be U1 prime and U2 prime. Now, if I know F2x prime, I can use that to find the axial stress in the bar element. So the axial stress in the bar element, sigma, may be expressed as F2x prime divided by the area. Okay, if I write an equation for F2x prime, I can write it as equal to AE over L times minus 1 and 1 multiplied by U1 prime and U2 prime. Sigma then would be equal to, if I divide by A, I get E over L times minus 1, 1 multiplied by U1 prime, U2 prime. Now we were able to relate the prime displacements to the global displacements, D. If I write here the prime as a 2 by 1, and I have D as a 4 by 1, then I will use this T star that we just were looking at. Transformation matrix, which is a 2 by 4. So if I use this D prime to substitute for U1 prime, U2 prime, we can write sigma then is equal to E over L multiplied by minus 1 and 1 multiplied by T star times D. If I take this portion here and make it a C prime, where C prime is a 1/4. Because this is 1/2 multiplied by a 2/4. So I get a 1/4, right? So this is clearly here a 1/2, and this is a 2/4. I can say that sigma for a bar element is equal to this C prime multiplied by the nodal displacements of the element with respect to the global axis. So I can say here where C prime is equal to E over L times -1, 1 times T star, which is CS 0, 0, 0, 0, CS. If I simplify, I can say that C prime is equal to E over L multiplied by minus C minus S, C, and S. So once we have the nodal displacements, I do not have, the reason we're doing this, we do not need to calculate the element forces to find the stresses in the bar, if this is all what we care for. I can use the displacements and C prime to directly find the stress in the bar elements. Let's work an example. I can use F1, but put a negative sign. Because you see F1 prime is showing as compression. Because I want to refer to the stress, a positive stress. Yes. Good. So we're going to look at a plane truss. So we can use the bar elements. And when I say truss, how can we define a truss?
Forces only act tension and compression.
Okay, so the members only tension and compression. We refer to these as two-force members. And specifically for a truss is composed of only two force members that are joint connected with loads applied only at the joints. We always have in mind these triangular shapes, but really this is the definition of a truss. So what I'm going to put in paper now does not look like the typical truss we have in mind, but it is an assemblage of some bar elements. Again, keep things simple, help us to focus on the finite element method and the procedures that we are trying to learn. So I'm going to look here at a vertical member that is connected to a horizontal member. This is 10 feet. This is 10 feet. And and here we have one that goes at an angle 45 degrees. And all these members are pin connected. So we have 3 members. And at this free joint, we have a downward vertical force of 10K. we are given that E is equal to 30 times 10 to the power 6 psi. A for all the members is 2 square inch. And we want to find sigma in all members. And I want to use this example to establish the procedure that we're going to follow to solve like problems using the finite element method. Remember these steps? We're going to put them in practice. Okay, so we're going to follow along these steps. Discretize and select the element type. If I look at this, we are using what type of element? Bar element. Discretize is very easy because it's made of an assemblage of pieces. So I can just make each piece of them an element. And I want to label the nodes and the elements in order for me to write the element stiffness matrices. I want to say here for step 2 and step 3, this is what we've been doing in this chapter. We've already selected displacement function and we drove the element relationship. So I can go right away to write the element stiffness matrices. So that's going to be my goal, is to write the element stiffness matrices. But in order for me to do that, I need to label the global axis, the local axis for each element, the node numbers, right? So I want to create my mesh. So let's start with this. Of course, if we are working here in plane, I'm going to refer to the global. So I'm going to put here the solution. We want to put the global axis. So we're going to use X and Y. Working in plane. Next, we want to discretize or create the mesh. So I want to label the nodes and elements. And when it comes to elements, I also care about the local axis for each element. Elements slash local axis. So I'm going to come here and look at my structure. And I also want to plan ahead. When we solve equations and apply boundary conditions, usually we were able to cancel or delete the rows and column corresponding to a restraint. So I look, here is a restraint, here is a restraint, here is a restraint. So these are my nodes, clearly. These are my nodes. I have 4 nodes, 3 of them are restrained. In order to make the elimination easy, I want to keep this at the top and this at the bottom. So I'm going to call this 1. I'm going to make this 2. I'm going to make this 3 and this 4. And this will make more sense when we write the equations. Okay. I'm going to define element 1, element 2, and element 3. So element 1 extends between 1 and 2. So for element 1, I will have an x prime that is going in this direction, x1 prime. Element 2 is going to have an x2 prime going in this direction. And element 3 is going to get an x3 prime going in this direction. Now, why is it important to identify the direction? Because when I write my element stiffness matrices, we have all these cosines and sines. So it would make a difference if this was going up versus going down. So it's not just a vertical member, but direction does matter. All right. If this is 10 and this is 10, we can see that this is a 45-degree angle.
Assuming the force was loaded, where the 10K was loaded.
The 10K is going downwards?
Assuming it was loaded upwards, does it mean the direction of the X1 will change?
No.
Okay, it's coming.
Independent. Yeah. And by the way, this is not the only solution. This is the one I choose to make the solution simple. But I can make it difficult on myself, still get the same answer. All right? Okay. So now we have labeled all the elements. And our next step, so we've done this step here, we've done the second step. Now next, I want to write element stiffness matrices with respect to the global axis. Which are X and Y. Okay. Now each of these matrices, K, is going to be equal to this lambda minus lambda minus lambda and lambda, where lambda is equal to, as we started today, C squared, CS, CS, and S squared. So clearly, for each of the elements, I need C squared, CS, and S squared. Yeah, oops, sorry. Thank you for catching this. Good. Just as a way of organizing the work, I'm gonna make like a table, and I'm gonna put element 1, element 2, and element 3. So this is the element number. And for each of these elements, I'm going to define theta. So for element 1, this is x prime going up. So theta is a plus 90 degrees. For element 2, theta is 45 degrees. And for element 3, theta is 0 degrees. I'm going to define my cosine, my sine, my cosine squared, my sine squared, and cosine sine. So the cosine of 90 degrees is a 0, the sine is a 1, cosine squared would be 0, sine squared is a 1, cosine sine would be 0. For 45 degrees, the cosine is the square root of 2 over 2, and the sine is also square root of 2 over 2. Cosine squared would be 1/2. And the sine squared will be 1/2. Cosine sine would be a 1/2. For 0 degree, the cosine would be 1, sine would be 0, cosine squared would be 1, sine squared is 0, cosine sine is 0. So now we are ready to use these and the lambdas to write the element stiffness matrices. So I'm going to start with element 1. So I'm going to have here K for element 1 is equal to EA times L. So I have here the 2 times 30 times 10 to the power 6 divided by the length, which is 10 times 12. Multiply by I have here the C squared is a 0. The CS is 0. So I have a 0. And then I have an S squared, which is a 1. Right? And this is going to repeat here 0, 0, 0 minus 1, 0, 0, 0 minus 1, 0, 0, 0, 1. Yes. Savannah.
Thank you.
And as I'm looking at element 1 extends from 1 and 2. Now, because we're looking at bar elements in plane, each node is going to have how many degrees of freedom? 2, right? So I'm going to have here a U1, V1. I'm going to have here a U2, V2. I'm going to have here a U3, V3. And here I'm going to have a U4, V4. So for element 1, if I want to label this local stiffness matrix with degrees, corresponding degrees of freedom, I will put here U1, V1, U2, V2, U1, V1, U2, and V2. Correct? Next, I'm going to go to element 2. So I have here a K for element 2 equal to EA over L. So A remains the same times 30 times 10 to the power 6 divided by the length. This is 10, this is 10, this is 45. So this is 10 square root of 2, the length, right? So I get here 10 times the square root of 2 times 12 to go to inches. And this is multiplied by, and I'm going to use my table. So I look at C squared. So I have a half. CS is a half. So here I have a half. And S squared is also a half. And I'm going to repeat. So I have here a minus half, minus half, minus half, minus half, minus half, minus half, and so on. And here we have positive halves. Now, element 2 extends from node 1 to node 3, which corresponds to U1, V1, U3, V3. So if I want to label this, I will put here U1, V1, U3, V3, U1, V1, U3, V3. Next, we're going to look at element 3. Okay, 3. And this is element 3. It's 10 feet long. Area is 2 square inch. Same modulus of elasticity. And here is my table for my cosine sines. So I will get a 2 times 30 times 10 to the power 6 divided by the 10 times 12. And then I'm going to put my stiffness matrix. Cosine squared is a 1. Cosine sine is a 0. So I have a 0, and sine squared is a 0. So here we have a minus 1, 0, 0, 0, minus 1, 0, 0, 0, 1, 0, 0, 0. I'm going to label the degrees of freedom that correspond to the third element. So I have U1, V1, U4, V4. This is a U. And U1, V1, U4, V4. And the next step, since I now have all my element stiffness matrices, and remember, we're going through all that to write them with respect to the global axis. So now all 3 element stiffness matrices reference one coordinate system. Now I can use the direct method to assemble them together. So we're going to use the direct stiffness method to assemble the global stiffness matrix K. And as I do that, can I figure out the order of K? Four by 4? Why? There are 4 nodes. Each node has 2 degrees of freedom. So this K is going to be 8 by 8, right? 8 by 8. How do we assemble K? Is equal to the sum from E equal 1 to 3, because we have 3 elements, of K E. So now I need to make sure I have an 8 by 8 space to write my stiffness matrix. Now, looking at these here, we can take a 2 by 30. So that's like 2 times 30 times 10 to the power 6 divided by 10 times 12. We take this as a common factor. Sorry. And then we have to create a table of an 8 by 8.
The other element was having a different length. Was having 10
Let's look at the elements. You see element 1
element 2, the L
is 10 divided by the square root of
2, yeah.
times the square root of 2.
Yeah. So now if you are taking the general length, what happens to that?
I'm going to have to include that in my matrix. So I just took a common factor,
Okay.
but I'm going to have to keep in mind the square root of 2.
Okay.
Right? So basically all these elements, Tarzan, are going to be divided by the square root of 2. Correct? So I'm going to start here by looking at an 8 by 8. 1, 2, 3, 4, 5, 6, 7, 8. So the first here, this is U1, V1, U2, V2, U3, V3, U4, V4. And where do you expect the majority of non-zero entries to be? Over here. And we're going to have a bunch of zeros on the sides of the diagram. So let's try to assemble that. I'm going to look at the contribution. If I look at, may I just zoom out a little bit so you can see? Is this still readable? Okay. So I'm looking here. Yeah, let me mark my columns as well. Okay, so I'm going to start here by looking at U1, U1. I have a 0 and 1/2 divided by square root of 2, right? And then I have here a 1, correct? So we have a 1 and we have 1/2 times the square root of 2. If I multiply by two here, but actually if we even multiply by a 4 to simplify that, I can write that as 4 plus the square root of 2 divided by 4 for the first entry. And then for the second, I'm looking at U1, V1. So I'm looking at a 0, again, 1/2 divided by the square root of 2 and a 0. So I'm going to write that as square root of 2 divided by 4. So this is U1, V1, and we're going to move on to U2, V2, U3, V3, U4, V4. Okay. U1, U2, I have a 0. Again, I have the minus 1/square root of 2 times 2, which I'm going to write it as, and then I have here, don't have any contribution from the, no, actually, this is U1, U3. So basically, this is going to be a 0. And then I'm looking at U1, V2, which is a 0. Here is this contribution that's going to come. And this is going to come as minus 2 divided by, minus the square root of 2 divided by 4. And then I have a U1 V3, which is also a minus the square root of 2 divided by 4. And then I have for U1 U4, I have a minus 1, and U1 V4, I have a 0. Okay. Let's move to the second line. Of course, if symmetry applied, this is going to be the square root of 2 divided by 4. And then for the V1, I have a 1, and again, plus a half, and this is all what I have. So this is going to be similar to this. So I got 4 plus the square root of 2 divided by 4. V1 U2 is a 0. V1 V2 is a minus 1. V1 U3 is a minus half, but there is the square root of 2. So again, we're going to write it as minus the square root of 2 divided by 4. V1 V3 is the same, minus the square root of 2 divided by 4. And then V1 U4 is a 0. And V1 V4 is a 0. Are you following the steps? Okay. Things are going to get easier as I move to U2. The only one that is contributing here is element 1, and it's all zeros. So I get U2 is a 0, and U2 V2 is a 0. And none of the others are contributing, so I get 0, 0, 0, and 0. Next, I go to the V2 line.
Did you fill in U1?
I did not, because I'm going to rely on symmetry. So V2, I'm looking at V2, and I have here a 1. And then I have zeros. Next, I'm going to U3. And I'm looking at U3, where again I have this square root of 2 divided by 4. And U3, V3, I also have a square root of 2 divided by 4, positive. U3, U4 is a 0. U3, V4 is a 0. Next, I go to V3, and I'm looking at V3, and I get a positive square root of 2 divided by 4. And then I have 2 zeros. And then U4, I get a 1. And U4, V4, I get a 0. And V4, I have a 0. Now this is my positive diagonal. And it's very easy for me to fill in everything below the diagonal using symmetry. So now I have the global stiffness matrix K. We're going to use K to write the global stiffness equations as F 8 by 1 equals to K, which is 8 by 8, times D, which is 8 by 1. Now, what is this going to look like? If I look at the matrix of the external forces F, I have an applied force 10K at node 1 in the y direction. And then for each of the other nodes, I have an unknown reaction components. Now, we do not have a force acting in the direction of U1. So I can write my force matrix, this 8 by 1. I can write it as 0 minus 10,000 pounds Then I have here the unknown support reactions. So I'm going to have an F2x, F2y, F3x, F3y, F4x, and F4y. So this here represents my F matrix multiplied by this big 8 by 8. Equal to this 8 by 8 multiplied by the displacement matrix. And this displacement matrix is going to include the unknown displacements as well as the prescribed displacements. So I'm looking here at my diagram, and yes, I have an unknown U1, unknown V1, but then if you look at all the others are equal to zeros. So what I did here is I wrote my global stiffness equations as well as I applied my boundary conditions. Now, because of all these zeros, I can reduce or write my modified stiffness equations by crossing the lines, the rows and columns corresponding to all the zeros. So really, I'm going to be left up with this top 4 by 4 portion. So when we apply, 1, 2, 3, 4, 5, 6. Stops here. So apply the boundary conditions to get the modified global stiffness equations. So now I'm looking at a 0 and a minus 10,000 equal to, and I'm going to borrow here from my global stiffness matrix. I have a 2 times 30 times 10 to the 6 divided by 10 times 12 multiplied by this 4 plus the square root of 2 over 4. And then I have the square root of 2 over 4. I have here the square root of 2 over 4. And I have here the 4 plus the square root of 2 over 4 multiplied by the unknown nodal displacements U1 and V1. So I have 2 equations and 2 unknowns. that we can solve to find that U1 is equal to 0.414 times 10 to the minus 2 inches, and V1 is equal to minus 1.59 times 10 to the minus 2 inches. Now, we're not just crunching numbers, but we want to make sure our numbers make sense. So if I look at my problem, I have the 10 kip applied downwards. Using my engineering imagination, when this structure deforms, is it going to be moving upwards, downwards, pull to the left, or pull to the right? Downwards for sure is going to be the majority of the components. Look at the displacement. I get a minus 1.59, and I got less than 1/3 of that going in the X direction. As we pull, it's going to rotate some, and it's going to tend to tilt towards the right. I always encourage you, when using the finite element method, to use your engineering imagination and judgment to examine your answers, because it is very easy to do mistakes. So we don't just want to provide numbers, but we want to make sure our numbers make sense. Okay, now our goal is to find the axial stresses in all the members. So now I have found U1 and V1, and all other displacements are 0. Now I can find the axial stress in all the members. Okay, so stresses in the bar elements the equation is sigma equal to this C prime multiplied by D. And we're going to repeat that for each element. So C prime is equal to E over L times minus C minus S plus C and plus S. So I'm going to apply it to element 1. I'm going to have this sigma 1 that is equal to E is 30 times 10 to the power 6. L is 10 multiplied by, from the table, if you look here, at a minus C, C is 0, so I get a 0. And then S is a 1, so minus 1. And then I have a 0 and a 1. And I'm going to multiply this by how many displacements? Remember, this is a 1/4. We're going to multiply it by the 4 displacement expressed with respect to the global system. So I'm going to get here the 0.414 times 10 to the minus 2, the minus 1.59 times 10 to the minus 2, and I have a 0 and a 0. And please remember, the outcome of this multiplication is one number only, is a scalar, right? So I get here sigma for element 1 equals to a positive 3,975 psi. So element 1 is in tension, which makes sense. So next we go to element 2. And a sigma 2 is going to be equal to E is still 30 times 10 to the power 6. Now L I'm sorry, I forgot here to multiply by 12. Please correct that. Because L is in feet. So for element 2, the length is 10 square root of 2 times 12 multiplied by minus C. That will be minus the square root of 2 over 2 minus S is minus the square root of 2 over 2 plus C square root of 2 over 2 and a plus S the square root of 2 over 2. Now again, element 2 extends from 1 to 3. So it is its nodal displacements are going to be U1, V1. So again, 0.414 times 10 to the minus 2 minus 1.59 times 10 to the minus 2. And U3, V3 are also zeros. And the outcome here would be U2 equals to 1,470 PSI.
We can see the
Sorry. So it is also in tension, but it does not get as much tension as the first element. And finally, element 3, we do a sigma 3 equals to E is still 30 times 10 to the power 6, and the length is 10 times 12 multiplied by. For element 3, C is 1 and S is 0. So I get a minus 1, 0, 1, 0 multiplied by the nodal displacement. Again, element 3 connects node 1 to node 4. So I'm going to have U1, V1, and U4, V4, which are zeros. When I do the numbers, we get here a sigma 3 that is equal to minus 1,035 PSI. So the bottom chord is in compression. If for any reason the numbers did not make sense, I can check as a validation equilibrium, for example, of joint 1 or node 1. This is for validation, right? So if I look at node 1, node 1 has a 10,000 force applied downwards. And then we get T1, a T2, and the compression here, T3. And the sum of the forces in the x direction should be equal to 0. So let's check. In the x direction, I have only components. I have a T3 and the component of T2. So T3 is going in the negative direction. So I have minus, and I have here for T3, we have this 1035 multiplied by the area, which is 2 square inch, plus I have the T2 component. So I have the 1470 times 2 multiplied by the square root of 2 over 2. When you add these two, you almost get a 0. The other equation of equilibrium would be sum of the forces in the y direction equal to 0. And when you look in the y direction, I have a minus 10,000 plus a T1, and sigma 1 was 3 975 times 2 for the area, plus the contribution of T2, which is a 1470 times 2, multiplied by the square root of 2 over 2. Again, when you do the math, you'll find that these are approximately 0. So this is used for validation. I hope now you can see why when I labeled, I picked this only free joint, I labeled it number 1. So that when I wrote my equations, I had my 2 unknown displacement at the top, and it was easy to eliminate the 6 lower rows and 6 columns to the right. Any questions about this example problem? You need to write. If I just review quickly the steps, we started by selecting the element, discretizing or creating the mesh, labeling the nodes and the elements, the global axis as well as the local axis for each element. We then wrote the element stiffness matrices. We used the direct method to assemble the global stiffness matrix. We applied boundary condition. We solved for the unknown displacements. Once we have all the displacements defined, we use the stress equation for a bar element to find stresses in each element. In the remaining 11 minutes, let's try to see if we can do another example with a hybrid mesh. A hybrid mesh, meaning I have different types of elements. We're going to mix between bars and springs. Okay. At least let's get started. So we have a 10-meter long horizontal element that is pinned at one end and supported on a spring on the other end, as well as a strut that is 5 meters long. And makes an angle 45 degrees. We are given E of 210 gigapascal. The area is equal to 5 times 10 to the minus 4 square meters. K for the spring is equal to 200 kilonewton per meter. And we want to find the stress sigma in the bar members. And I know the time is not going to may not allow us to finish it all, but at least let's set up how we're going to approach this problem. So as we did with the previous example, we are going to identify the global axis. Again, in this case, we're going to have X horizontal and Y vertical.
Any loading on the system?
Thank you. We're going to put a 25 kilonewton at this free end. Next, we want to discretize. So we want to come up with a mesh. So looking at it right away, you probably see why I meant this is hybrid, because we have bars and then we have this spring. So we are looking at hybrid mesh, bars, and a spring. Now, when I want to come up with a mesh, one of the first thing here, I want to label my elements and my nodes. Okay, my elements again are obvious. I have 2 bar elements and a spring element. And I don't think the order is going to matter, so I'm going to call this 1, 2, and 3. Really, what's going to matter is labeling the nodes. So again, we can use the same trick we did for the previous example and look at the node that is free and make it node 1. So I'm going to make this node 1. And then we're going to go in some sort of an order. So I go like for element 1 is 1, 2, element 2 would be 1, 3, and element 3 would be 1, 4. Next, I want to identify the local axis for each element. So element 1, I'm going to go like this is x1 prime. Element 2, I'm going to call this x2 prime. And element 4, we're going to call this, or I'm sorry, element 3, I'm going to call this x3 prime. So here we identified elements, labeled nodes, and local element local axis, local element axis. In this case here, we had the x1 prime, x2 prime, and x3 prime. We are working in the xy plane. We have 2 degrees of freedom per node. We have a total of 4 nodes, yes, 4 times 2 equals to 8 degrees of freedom. 6 of them, 6 of which are restrained. Therefore, 2 unknown degrees of freedom. I think this is a key to the solution. Next, we're going to write the element stiffness matrices with respect to the global axis, X and Y. So we are going to define the cosine, sines, cosine square, cosine sine, like we did previously. And then we're going to use the direct method to assemble And when we assemble the global stiffness matrix, we really know from the previous example that we care about the modified portion, which is going to be where the modified, if I'm going to have like 2, 3, and 4, the 6 degrees of freedom going to be equal to 0. So I really care about the contribution I'm getting towards U1, V1. So here we are going to have a U1 and a V1. These are the unknown displacements. So for each member, I'm going to get contribution towards U1, V1. And these are the ones we want to take into consideration. As a matter of fact, for the spring, how would we write the one for the spring? Maybe I should pick on this one and write it down. So for the spring element, we are always used to this K equals to K, and then this is the prime, right? And then we have the 1, minus 1, minus 1, and 1. So this is with respect to x3 prime. Now, if I look at the angle here, I can think of this as going in a negative 90 degrees, right? And I can use exactly the same method we did before, but instead of EA over L, I will be looking at using K, right? So K for the spring will be equal to K, and then we would be looking at, now specifically for the spring here, I'm looking at U1, V1, U4, V4. And the ones I really need are the one that contributes to U1, V1, which is this here. And when you apply the transformation, you will find that I will get a 0 and a 0 and a 0 and a 1, because the spring is contributing to the vertical direction, right? So you see the stiffness here is going to in the V1 direction, and all the others are 0. Of course, if you are to continue this, you will get like 0, 0, 0, minus 1, 0, 0, 0, minus 1, 0, 0, 0, and 1. But what's going into the global stiffness matrix would be this portion here, right? For other elements, you're going to follow exactly the same steps. And then you want to come up with the K modified. That is the 2 by 2. So you get contribution from all the elements, and then you get this 2 by 2 stiffness matrix corresponding to U1, V1, U1, V1. You use the modified global stiffness equations to solve for U1 and V1, and you will find that U1 is equal to minus 1.724 millimeters, and V1 is equal to minus 3.448 millimeters. I will be happy to post these or go over it again when we meet again, but I encourage you to try it at home and challenge yourself and see if you will get these answers. Now, once you have U1 and V1, you should be able to easily calculate the stresses in the bars. So please try to work on this at home And when we come back on Thursday, I'll be happy to answer any questions. Okay?